Hi folks, welcome to chapter 6 and the similarity of polygons. So we're going to talk about different polygons in this thing, and what we're going to talk about the word similar. And similar means a very specific thing in mathematics. It doesn't mean almost the same like it does in common English. What it means is that it is exactly the same shape, but it might be a different size. So a couple of things that will tell you if a polygon is similar, and these both have to be true for similarity to be present. They have the same shape, different sizes. In similar polygons, corresponding angles are the same size. So any matching angles. So for example, we've got angle A and angle W. They're going to have to be the same size for this to be a similar triangle. Similarly, B and X, C and Y, D and Z all have to be similar. If every single angle in your shapes is similar, then you might have similar polygons, or is the same. You might have similar polygons. The other thing that has to be true is that all corresponding or matching sides have to be similar or proportional. So say WZ is twice as big as AD, then every other pair of matching lines in this quadrilateral will have to be twice as big. So ZY would be twice as big as DC. XY would be twice as big as BC. WX would be twice as big as AB. So all the angles have to be exactly the same size, and all the sides, when you compare the same sides or similar sides together, have to be in the same ratio, or we might say proportion, or you might say they have the same scale factor, which could be 2 to 1, or it could be some other scale factor. So, as I was saying, that means that angle A has to be equal to angle W, and line AB is going to be proportional to line WX. And BC will be proportional to XY with the same proportion, etc. All right, so here's an example, page 255. What can we do with similarity? One thing that is similar is scale drawings. Scale drawings are always done to be similar. So all the angles should match the actual angles in real life, and all the sides should be reduced by the same scale factor. In this case, we've got the longest wall of this room is actually 12.75 feet long. How long are the other walls? So how are we going to figure this out? Well, first we got to identify the longest wall. That's this one. That's 8.5 inches, right? 12.75 feet is what the real measurement is. So from that we can determine our scale factor. Scale factor is the number that we multiply everything by to get to the real size, or the number we divide everything by to shrink it down into a scale drawing. Find out what it is. We divide 12.75 feet by 8.5 inches. Mistake. And just a minute, let me grab my calculator for that. 12.75 divided by 8.5 equals 1.5. The scale factor is not actually 1.5. It's 1.5 feet per inch, because we have different units, top and bottom. But that means that if we divide, or if we multiply any of these values in inches by 1.5, we're going to get to our value in feet. So let's do that. 3.4 times 1.5, that's going to be 5.1 feet long. 2 inches times 1.5 equals 3 feet long, and that's this little side here. 2.6 inches times 1.5 is 3.9 feet long. 6.5 inches That's going to be 9.75 feet long, and 6 inches times 1.5 is going to be 9 feet long. I'm just going to need to pause a moment to recalibrate, so I'll be right back.